I think the microphone is working. Can I have your attention, please? Good afternoon. Welcome to the class. We are beginning our journey to the network layer next. The third from the top of the 4 layers we're going to see in this course in detail, right? We're not going to really go to the physical layer, application, transport, network. We're done with the transport layer session. We're running a little bit, by the way, behind on the conceptual material. I'm not quite certain what I'm doing differently. It might just be the size of the class, maybe a few more questions, maybe a little more time on clicker questions, where I go back, spend more time, because I feel like that's needed. So I'll be assigning small portions here and there for just reading by yourself, especially ones that I think will benefit or don't particularly benefit from whiteboard calculations, problems like I show you. So in the transport layer section, I didn't really say much about QUIC, which is Google's transport protocol. That's essentially like what you're implementing in Spirit in your programming assignment 2, project 2. QUIC is Google's reliable transport on top of HTTP, right? You've seen QUIC a little bit in the HTTP section. The textbook will tell you how QUIC is a little bit more about QUIC's implementation details, about its default implementation, default support for transport layer security. So you'll have a slightly better appreciation of how QUIC is being used in HTTP. In HTTP 3, like we very barely alluded to in the application layer section by reading the chapter, right? So that's for self-reading. All right, so what's in the network layer? We're going to look at what the network layer has, its high-level functionality, its decomposition into control and data, the control plane and the data plane, which is at a high level the logical decomposition of network functionality. We'll go a little bit deeper into what exactly is inside of a router, right? You've played with transport, well, you've played with application layer stuff. You can reasonably imagine how transport layer protocols are implemented inside the kernel. You're in fact implementing one in project 2 at the application layer. But most of you probably haven't seen a router, and that sort of might seem a little bit like a mysterious object. So we'll take the mystery out, some of that at least. Okay. So as before, we're going to go in terms of principles and practice. We're going to see conceptual principles for how these things, network layer protocols, network layer devices are put together, and then look at some examples of how actual protocols, of course, IP being the most important one, what function it consists of. All right, so let's start with the high-level decomposition, data and control plane, right? What do these things mean? Data and control plane. That's where we'll start. We'll skip over this to, all right. So here's a high-level overview, pictorial overview of the network layer. We saw a similar picture for the application layer and the transport layer. The transport layer, we said, was fairly simple to understand, right? What does the transport layer do? It encapsulates, decapsulates packets with segments with transport layer headers. UDP wasn't doing very much, just attached source port, destination port, and one more checksum on top of an IP datagram. TCP did, unlike UDP, quite a few things, right? At the network layer, this is the third of the 5-layered stack. The network layer protocol exists on every device, on every router along the path, as well as at end hosts. Okay? The end hosts have all the layers. Network layer devices or routers will process packets only up to the network layer, up to and including the network layer. Routers are going to examine what are they going to do at the network layer. They're going to examine header fields in these datagrams that are passing through. They're going to datagrams, what is the term we use at the network layer, segments is the term we use at the transport layer, right? The main function of one single router is to take a packet or datagram that arrives at one of the input ports of a router and send it on fairly simple, but a lot of intelligence goes into how to do this correctly and how to do this well in a way that's efficient. Okay. Control and data planes are associated with verbs that are respectively forwarding and routing. Forwarding is the task that happens at line speed. This task of taking a packet that comes on an input port and deciding which output port it has to go to and then sending it on that output port. That task is called forwarding. This has to happen at line speed, blazing fast, right? Because if you have 10 Gbps, 100 Gbps links, packets are arriving really fast. You have barely nanoseconds or less to spend on a packet. So this has to happen really, really fast. That's forwarding. It's also called the forwarding plane. And forwarding plane is also just one more term for the data plane. Data plane, forwarding plane, these are used interchangeably. Control plane, routing plane, they're used interchangeably, right? So routing is what the control plane does. Forwarding is what the data plane does. That's your terminology. Routing is sort of more algorithmic, okay? There's more algorithms, graph theoretic algorithms, of the kind you've actually seen, right? In your algorithms courses, 311 is that where I'm guessing you've probably seen Dijkstra's algorithm, right? Shortest path computation, right? So Google Maps is using that. Internet routers use algorithms like that, right? Shortest path computation. Just what is shortest? The meaning of that is very different in transport and road networks versus internet-like networks. We'll see what shortest means exactly. So you'll see algorithms like this in the routing plane. For some time now, this logical separation between data and control has grown very significant in the last decade. In fact, it's grown from like a logical or a software level separation to a physical separation between data plane and control planes, to the extent that a control plane can actually be located in a data center in the cloud somewhere controlling the entire network. And so consistent with this technology trend, that's called software-defined networking, that's been around for about a good decade now, the textbook has sort of split the network layer chapter into 2 chapters, because that's actually a good way to understand it, into the data plane, which is what we're looking at first, and the control plane, where the routing algorithms reside, which we'll look at in chapter 5 in the textbook, right? Okay, so the analogy to road trips, this is if analogies help, forwarding is what you do at every single interchange or toll booth, if you will, and routing is the Google Maps, right? Planning the trip while you're at home. Routing is a slow process, forwarding is a blazing fast process. Okay? So think of routing as a background process that's constantly running, but it doesn't have critical time constraints, speed constraints like forwarding actions do. Okay? So here's what happens in the data plane when at every single router a datagram arrives at one of the input ports. So those green things are arriving into a buffer. The headers in those datagrams are what will be inspected by this router in order to determine if this packet arrives at this input port destined to this destination IP address, which output port should it go to, right? Control plane is implementing the network-wide logic, which means all the routers are coordinating in the background relatively slowly and determining what goes into the forwarding table of every single router. So collectively they are determining what this one router's actions, input to output port matching actions, should be. They're both happening in parallel all the time. Okay? There's 2 ways in which we can do control plane actions. There's traditional routing algorithms that will use Dijkstra-like algorithms for doing shortest path computation, and then that's a separate process that's running inside the router. So that's a coordinated routing distributed routing algorithm. And then as soon as the computation is finished, this router will populate its local table to say, okay, if the packet comes like this, destined there, then send it on that output port and so on. The more modern approach, which I said is software-defined networking, that's been around for a good decade or a little more than that now, it has a greater separation of this control and data plane. Instead of both being located on the same machine and there just being a logical separation, a software level separation, there's a much greater level of separation between these two layers. Okay? To the extent that you can, it's sort of like a remote control. You get a global view of the entire network, and management of the entire network becomes easier. So the motivation for software-defined networking actually came from network operators who had a really difficult time managing complex networks. It's not easy to manage complex networks in an entirely distributed manner. So that's where the motivation came from, the management of the operator community. So what are the, let's zoom one more level deeper into the separation I'm talking about. What do I mean by this logical separation that always existed, which is how we always thought of and taught networking, to this more explicit separation or physical separation I'm talking about that's been around for about a decade, right? This is the latest new trend in networking. So this is our traditional approach, per router control plane. Every single router has its own control plane, right? The logical separation. Think of let's zoom out every single router into two parts. Some of the software in the router, these routers run operating systems, just like your laptop, my laptop, and other machines run operating systems. These router operating systems they are designed to do different things than a typical machine does, than a typical PC does, right? So if you zoom into one of these routers, this traditional per router control plane, where every single router has its own control plane, this is what the picture looks like. Each router has this forwarding table. The forwarding table can have many things in general. It has two very important columns in order to determine which output port a packet needs to go to, right? So in this picture, it shows you there's a header column and there's an output port column. So in the traditional routing or forwarding world, you can think of really the header column as the destination IP address, or some pattern matching a destination IP address. A regular expression that says if the destination IP address looks like this, it's sort of going to 128.119, which is a prefix owned by UMass. Then a router in Denver might say, okay, set it on my output port 5. So in the traditional world, you would basically look primarily at the destination IP address and then decide what the output port is. That's your forwarding table. The more general approach will take this will extend this. This generalized forwarding approach will extend this to not look just at the destination IP address, but other parts of the header as well. Okay, we're still looking at the per router control plane. This forwarding table came about in every single router because these routers ran this distributed coordinated algorithm in the background, right? They don't need to run at nanosecond speed. And after running this distributed algorithm, every router has the answer to what its forwarding table should be. These forwarding tables better be consistent. There has to be coordination in the routers. If they're not consistent, you can run into trouble. Like, what if, say, this router says, okay, to get to Google, and Google's IP prefix, I need to set it on output port 3. And then this router has a forwarding table that says, okay, if I get packets destined to Google, I need to set it on this output port, whatever this is. It's not numbered in this picture. What do you have? You have a loop, right? They'll be ping-ponging this packet forever. Actually, not forever until the TTL in the packet expires. It gets decremented at the top. Remember from chapter 1 where we learned traceroute, packet will eventually drop, resources will be wasted ping-pong, right? Loops may not just be one hop long, there could be a longer loop like this. So unless these forwarding tables are computed in a consistent manner, which requires this distributed algorithm that these guys are running, you can have problems, right? So that's our separation, that's our logical separation between data and control plane with a routing algorithm consistently computes these forwarding tables, feeds these into each router, and both pieces of code are running on the same machine. I think the sound is, hopefully we can ignore it. People can hear me okay, right? All right. Both pieces of code are running on every single router. One is a distributed algorithm, one is just a local forwarding action, right? This is how the world ran. Networking was until around 2010, roundabouts, for like a good 3 decades or more, right? Around this time, the end of the arts, is when we moved on to a new trend happened in networking. This is called software-defined networking. It's called software-defined networking, and there is some truth to the software-defined aspect. Like some things moved from hardware to software, but that's not the only part of it, right? Anytime you move things from hardware to software, it becomes much more programmable. Things implemented in hardware are more ossified and more static. They're faster because implemented in hardware, but then you can't change them unless it's programmable hardware, which is sort of a very specific class, like ASICs, for example. But if you move things into software, they become much more programmable. Programmability means much more flexibility for people who want to play with these things, right? So there is an element of software, moving from hardware to software and software-defined networking. But the more important component is the separation between data and control plane that moved from logical to physical. So compared to the previous picture where both pieces of code were running on every single router had a distributed piece of code, and every single router also was doing the forwarding. Here's what the picture looks like. We zoom into what's happening in every router. There's a data center in the cloud. This is where our remote control of the entire network exists. A smaller number of operators would be enough to manage this network. They would have an easier time managing this network. This is crazy. I hope something doesn't fall on us. I'm a little scared. Okay. The traditional option was to manage these networks was, from like an operator is still in one building, right? They'll be pinging routers independently. They'll be using a management protocol to get logs from different routers, construct a global view. This was all a pain, right? This is not easy to do. I'll try to speak up. I'll try to record that noise. This remote control approach is taking the whole network, constructing this global view that makes it much easier for these operators to have the view, change the view, manage the network thereby. Okay? So now the control plane, instead of running a significant portion of it running in every single router, is largely running at one place in a centralized placement data center. Again, I would say this is logically centralized. It doesn't mean there's one server on which all the control is running, because if that server crashes, you have a problem. It's fault tolerant, but it's big fault tolerant within a data center or maybe adjacent data centers for building level protection. But it's largely physically at one place. That's the benefit you get. All of the management can happen in this remote controlled manner. So as before, you still need forwarding tables for every single router. For that purpose, every single router still has some small element of control. That's called a control agent, a CA at every router, that communicates with this data center. That data center is including running Dijkstra's algorithm. So this data center is running Dijkstra's algorithm. I'll just try to be as loud as I can, all right? In the cloud, communicating with control agents every single router. That control agent fetches these forwarding tables, installs the forwarding tables, and now the separation between data and control has basically become physical, right? The amount of piece of code that's running on every router is just a lightweight control agent. It is not running a distributed algorithm. That algorithm is actually running a centralized place. Right? So that's a big difference, and it might be a bit hard for you to appreciate the significance of this because you haven't really tried to manage a large network. But operators who do this, their lives become a lot simpler. There's another huge benefit of this. Okay, this is a very, very important trend in the networking industry. It's innovation. In the previous world, the likes of Cisco, Juniper, Huawei used to, well, they still largely dominate the networking industry, the router industry. But they used to make these boxes that are siloed or verticals, where you buy the hardware and software entirely from one of these vendors, and then you're kind of locked into them. Right? It's not easy to mix and match in a market competitive manner gear from different networking vendors. They all support TCP/IP style protocols, but the implementation differences are different enough that management will become much more challenging if you bought gear from different vendors. What this is doing is stripping off the control software and allowing it to be run in the cloud. And there's open source versions of this control software. And so these routers have become much dumber switches now. They're forwarding boxes. They don't need to have sophisticated control algorithms. So you can go to a manufacturer like Broadcom that will just manufacture switches or switch chipsets. You can construct your own switch, get your control software from somebody else, or use open source control software. And this just leads to much more programmability, flexibility, growth, and innovation. Right? So this is why this trend is considered very important. It improves management. It has long-term implications for growth. Right? So let's move on to the SDN, software-defined networking trend, to looking at what are the service models that the network layer offers. We saw the transport layer that is TCP and UDP. There's other protocols, but we saw in great detail TCP and UDP. TCP gives you reliable devices. UDP gives you just There are some other protocols, but they'll offer some combination of reliability, rate control, lack there. You could ask the same question with the network layer. What network layer service can the transport or the application layer expect? Right? What are examples of network layer service models? You could say, I want guaranteed delivery from the network layer. Every single datagram sent by host should guaranteed be delivered to the other side, reliably delivered to the other side. If the network was already doing this for you, then we wouldn't need TCP. If we have TCP, we think it's best done at the ends. But there are networks which may go some ways to do retransmission internally to mitigate the effect of intermittent or en route losses, making the losses less visible to TCP, so TCP has an easier time dealing with them. So you can have some level of not guaranteed delivery in the internet, but loss mitigation within the network also. You can also ask, you can say, I want a Tony. I need a delay guarantee. I want every single datagram to be delivered reliably, and I want it delivered within 50 milliseconds. Okay, you can ask for many things. You can ask for flow level guarantees. These are datagram level guarantees. You can ask for flow level guarantees to say, my Zoom calls need a minimum of 2 megabits per second for good quality. So I want guaranteed bandwidth of 2 megabits per second. My connection, my flow should get a guaranteed bandwidth of that. You can ask for many things. Unfortunately, the internet gives you only a best effort datagram delivery service. Okay. What is best effort? Best effort, I've used this term before. It's a euphemism for sloppy or no effort, no guarantees. No guarantees, absolutely. It's the internet's IP layer, network layer, it's like UDP. You send a datagram, it sends just, UDP is literally just source port, destination port, and one more checksum added on top of IP. IP is very similar in spirit to what UDP gives applications. You send one datagram at a time, they are independently treated. You don't track flow statistics or any kind of offer any kind of flow guarantees. Packet may get there, if it get or not get there, if it gets there, there's no guarantees on how long it'll take. No ordering guarantees, reordering can happen as well. Okay? So that's the internet's best effort service model. It may seem like isn't the internet supposed to be really cool and powerful and functional? Why is it sloppy? Why doesn't it give me any kind of guarantees? Well, this is largely considered a feature, not a bug. This is considered one of the internet's biggest strengths. This is called minimalism. You don't embed functionality, unnecessarily complex functionality into the network. To get that functionality correctly, you need to implement it at the end host anyway. So reliability is a very good example of this. You can make every single link in the network very reliable, right? If this has a high loss rate, this will be end host. Communicating with another end host on the other side. You can work hard, engineer this link to be really, really loss tolerant. But at the end of the day, whatever you do here, it might go downstream to another ISP and the packets might get dropped here. You have no guarantees on what routers will do. So the only way for this end host communicating with this other end host across the internet to know that packets are going reliably is to have something like TCP running on the end hosts, to have end-to-end acknowledgements. That's when A can rest assured that the datagram is sent to B, got all the way there, the acknowledgement came all the way back here, now A can relax. So no matter how much you engineer, how much local retransmission you do across this link, to get reliable transport correctly, you have to do end-to-end reliability anyway. So there's diminishing value of over-engineering lower layers of the network protocol stack. This is often referred to as the end-to-end principle. It's a very, very powerful, important guiding design principle. It's not an exact rule, it's a heuristic, it's a principle that guides much of the internet's design philosophy. And so that suggests that don't work too hard at making these portions, don't over-engineer them. Push functionality to the end host. These end hosts are very powerful. They're computers. Today's laptops are like supercomputers from the 80s, right? So you can push that functionality, and for correctness, you kind of need to do it at the end anyway, right? So keeping the network layer minimal is a huge feature, not a bug of the internet, right? So you've seen that. So that said, there are networks that are different from the internet, that do provide some guarantees. Delay guarantees are generally the hardest to provide in any kind of a network. Okay, so ATM networks, these are circuit switched networks, asynchronous transfer mode. That's not your ATM machine. Asynchronous transfer mode is just a class of circuit switched networks, right? It came from telephony. Circuit switched networks, remember dedicated service. You reserve resources along the path. That's how they give you those kinds of guarantees. It is possible to get even delay guarantees with a very high probability. Anything can fail at any time at the end of the day. But in the common case, you can get delay guarantees as well if you reserve resources in advance in these circuit switch style networks. But they're the hardest to get right. They cost a lot, right? We've seen that anytime you dedicate resources can idle when they're not being used. Frequency division multiplexing, time division multiplexing. We've seen how resources can idle. We said the internet's packet switching gives us the benefits of statistical multiplexing, but queuing and congestion and no guarantees is the cost of all that. All right. Now all that said, it's not that the internet doesn't have, it completely eschews any sort of desire to provide any kind of guarantees. There are RFCs, there are standards, standardized protocols like INTSERV or DIFSERV that are listed here. that do go beyond best effort. These are not commonly used. To the extent they're used, they might be used within single networks. A network would use it to better manage resources within its own network, but you don't have end-to-end guarantees or prioritization of things stored for internet traffic today. So INTSERV basically gives you circuit-like functionality that allows you to reserve resources as call setup overhead, just like in circuit switch networks. DivServ is more like, it's lighter weight, it's not reserving resources, it's more like prioritization. It's saying these are gold packets, silver packets, bronze packets, they go in different queues, they get treated differently. Okay. So these are beyond best effort, or these give you better than best effort guarantees, or not guarantees in DivServ, at least prioritization. They're not commonly used. Okay? Best effort is what describes, is a de facto description of the internet's behavior. Right? People have gone back and forth on whether best effort is the best way to organize a network. You could look at, there's a bunch of reasons to think why best effort is indeed a great way to design a network. Okay? Back in, until even the 90s, there used to be a lot of debate on whether that's when INTSERV, DivServ, and all these better than best effort RFCs or things were being standardized, protocols were being standardized, and there used to be a lot of debate on, well, the internet gets congested, sometimes it's slow. Back then, bandwidths were much lower than what we have today. Video, which is, we're all so used to it, it wasn't easy. It wasn't easy even listening to streaming songs, like radio on top of the internet, without glitches. And so, people basically make strong arguments for, well, we need to build something more. Look at the telephone networks, calls are so smooth. They don't get dropped. Once you get in, you get it, your call is all smooth. We need to have reservations. We need support for reservation of resources. At the end of the day, best effort, you could say safely that it's one. Our current approach is to still get all the benefits of statistical multiplexing, back from chapter 1. The biggest thing that packet switching gives you. We didn't bother to change that. We didn't add circuits, reservations, or anything on top of that. And we simply said, we will just provision it with enough bandwidth so that all the applications have a fine time. So that the likelihood that there's too many users competing for resources just becomes very small. Remember that probability example we did in chapter 1? That's what ruled the day. That's what still rules the day in the internet. We also have other application level things like CDNs we saw in chapter 2, content distribution networks that move services closer to end users. There's multiple places you can get services from. So with enough capacity provisioning, with enough places to get services from, we don't really need guaranteed, we don't need any kind of performance guarantees. We don't need, therefore, any kind of dedicated resources or reservations. It also helps that unlike phone calls and also Zoom calls, okay, even though they run on IP, the bulkiest, the most bandwidth hungry of internet applications, they're elastic. They're like TCP. If you get a lot of bandwidth, they will transfer the bytes quickly. If there isn't a lot of bandwidth, they'll slow down, right? AIMD slows down, they're doing all the rate control. And that's okay, right? If a long download is happening, it'll take longer or not so long. It doesn't really come in the way of the application experience. But for phone calls, as well as video calls, it does come in the way. For real-time applications in general, real-time interactive applications that are delay sensitive, if it's not sufficiently provisioned, then we have a problem in packet switch networks. But we deal with that by throwing more money, more resources at the problem. That's what's won the day. Okay? It keeps the network very simple. Okay. Let's dive next into what's going on inside a router. Okay? That mysterious object. Routers, what are they doing? At line speed, they're matching packet headers to corresponding output ports. So they're shuttling packets from input ports to output ports. That's what they do most of the time. So those are the input ports on the left, output ports on the right. Connecting these input ports and output ports. So each one of these is like an Ethernet port on your machine. each one of those ports. They're connected by cables to similar ports on adjacent routers, or these routers might sometimes be the next city. So they could be long distance cables. They could be intercontinental cables. To be able to do this matching and forwarding at line speed from input to output requires a complex interconnection fabric in general. The design of this fabric, there's a lot of smarts going to it, there's different ways of doing it. This has to be at line speed, remember. It has to be really, really fast. There is a routing processor. This is just like, this is for compute. This is where the routing algorithm will be run. In the case of an SDN network, this will be fairly simple. There'll only be a control agent that communicates with the cloud, because it's cloud connection. And that's your logical separation between the routing plane or the control plane and the forwarding plane for the data. Forwarding, data, routing, control. So much of the complexity of a router lies here, okay, in the design of this fabric. But to understand that complexity at one more level of depth, let's zoom further into what's going on at one of those input ports. The first thing is a line termination point. So you can think of this as when you plug in an Ethernet cable into an Ethernet port and you hear that buzzing happy click, it's gotten there fine. That's your line termination point. That's your line that's hardware. That's where bits are coming into. At this point, there's link layer code that's the lower level, but below the network layer, which we haven't seen. That's going to assemble the frame. Frame, datagram, segment, equivalent terms. The link layer may seem very mundane, but there's fascinating algorithms that are needed even at the link layer, as we'll see. Okay? It's not simply just collecting bits and putting them into a packet. It's quite a bit more than that that goes on even there. But we're not going to see that right now. After this, once the link layer has done its job of constructing this receive frame, that's where the network layer processing is really going to start. That's where this task of forwarding, determining the output port. We're still in the input port right now, right? We've zoomed into the input port. It's going to use the header values to determine the output port. If packets arrive faster into this input port, then this fabric can process out of the input port to output ports. There'll be queuing at the input port. So queuing can actually happen at the input port or actually the output port as well. I'll show you that as well in a second. In between, there's processing happening. So this is another explanation for, or this is the explanation for why in chapter 1 I said queuing and processing, there isn't like a set in stone order that one happens before the other. Queuing and processing can happen multiple times inside the router, but at the end of queuing and processing, there's transmission and then propagation. That's always fixed. Those two are always at the end in that order. So input port queuing can happen if the fabric cannot push frames fast enough compared to the rate at which they're arriving in the link. How do you forward this? I said there's two kinds of forwardings. The old school and the SDN style forwarding, right? Which is doing generalized forwarding. Once you're moved to remote control and software-defined, programmable, flexible logic, you can do more generalized forwarding than just destination-based forwarding. So SDN and generalized forwarding go hand in hand. The traditional model was just look at the destination IP address, generalize, just look at everything in the header space and just in the header IP header fields and the, well, possibly TCP header fields as well, and decide how to determine or which output port it should go to. So let's look at just destination-based forwarding. It's been around for the longest time, and that's still largely what's done even today, right? In order to determine the output port, the single most important header field is the destination IP address. That's done as follows, right? Now we've zoomed into this forwarding table that's determining the output port based on the header value, get destination IP addresses. So these are IPv4 addresses. IPv4 addresses are 4 bytes or 32 bits long, like shown in this picture. And this has the two essential ingredients for forwarding table. The header value, in this case destination IP address, and the output port. So in this example it says, if your IP addresses lie in this range, go to output port 0, in the next range output port 1, output port 2, and if it doesn't match any of those ranges, the default is 3. Okay, anything that doesn't match one of those, just send them on 3. So this could be an example of, well, I have routes to go to this range of addresses, this range of addresses, this range of addresses. For anything else, I have my own provider. I'll send it to my provider ISP and they'll figure out how to do it. So that's one way to think of this. Sometimes you might want, your forwarding might not lend itself to nice range splits like this, like in this picture. You might want to do something like, all right, within that range, in that first row, I don't want all those packets going to output port 0, but I want most of them to go to 0, but then I want some of them to go to 3. Okay? So now you have an issue. If a packet comes in with a header field that lies in this range, but not in this range, you want it to go to 0, but if it lies in this range, you want it to go to 3. This is implemented using a concept called longest prefix matching. There are two rules that match an incoming packet in this range. This rule also matches. So anything that matches this rule will also match this rule, because this is a subset of the range of this one. When a packet matches more than one rule, which rule should we take as the determining rule? Well, the answer is longest prefix matching. This is the longer match rules the A is the answer. And that's how we do destination-based forwarding in the internet. Okay, that's called longest prefix matching. Looking for forwarding tables, use longest address prefix that match the destination address. So here's another example, okay, of IPv4 prefixes. The stars are wildcards, like in regular expressions. So this is saying if you're, oops. Okay, so this is saying there are 4 rules here. One's the default rule, and then there are 3 actual patterns here. So there's something interesting going on in this pattern. We can see here that this matches everything with, so these are all common. There's no difference here. Here it starts with 0, 0, 0, 1, 0. This goes on at 0, 0, 0, 1, 1. So anything that starts with 1, 1 cannot possibly match this 1, 0. But here's another rule that starts also with 1, 1, and then it's got stars here. These two rules are not mutually exclusive. So a packet can come in that starts with 1, 1, 0. It'll match this, it'll also match this. They're not mutually exclusive. Here's where longest prefix matching plays a role. Let's ask the question. The first packet, this example, which interface should this go to? This matches only one rule, right? So it matches only this rule, it doesn't match these other rules. So it has to go here. What about this one? That's the longest prefix matching rule. It matches both 1 and 2, but it's the longer match that we're going to take into account. So by that reasoning, it's going to go to 1. Okay? So that's fairly simple. Generalized forwarding is operating on more than just the destination IP header, destination IP address. And we'll see why how it's more complex and how it's implemented using more programmable or more flexible mechanisms. But longest prefix matching is still largely the default destination-based routing done using longest prefix matching. So that's fairly simple. Okay. How is this actually implemented? These are implemented using what are called as content addressable memories, CAMs. Specifically ternary CAMs, they're particularly effective for matching these kinds of patterns. They can do this in one clock cycle, therefore they can do these matching at speed. There's these kinds of memories. They're different from the memories, SRAMs that are used in our PCs. They're more expensive. And the number of entries that these memories have, they don't usually actually cross 1 million or so. Even even 1 million is a high bound. Most even core routers in the internet don't have more than 500,000 or so entries. We'll see where this number comes from, right? In IPv4, you can have 4 billion possible addresses. IPv6, you can have many more. But routers don't have an entry for every IP address. They have entries for these prefixes, which significantly cut down the space from 2 to 32, which is what 4 billion is, to about, barely 500K, right? So even those many entries is a fairly big number for the rates at which we want to do this kind of matching. So these memories are engineered specifically for doing that. Okay, so that's about destination-based forwarding. What about that fabric in between that I said? That's where the money is really. That's where routers really have much of their smarts. All the scheduling algorithm smarts are there. You really need that working blazing fast. So why is that problem even complex to begin with? Like what is the problem even? Like, you want to send packets from your infrastructure to understand that. And mathematically what's making this that complicated? Well, if you think about it, there's n squared possible combinations. There's n input ports, n output ports. So there's n squared possible combinations. The packet could arrive at any one of the input ports, be destined to any one of the output ports. So there's quadratic complexity in the logic. Okay, so mathematically or asymptotically, if it helps, that's why it's not easy to design this fabric. Okay. At the hardware level, it's like running lines from every single input port to every single output port. Okay, but that would be n squared lines. That's not easy to do, or that's costly to do. We want to minimize the cost of building this fabric while making it work at line speed. What does line speed mean? You have n input ports, each allowing packets to come in at a rate of r bits per second, n output ports allowing, let's say, r bits per second each. Ideally, you want to support nr total traffic coming through this. Okay. There shouldn't be a bottleneck inside this fabric. That's the problem we're trying to solve. And that can have quadratic complexity of matching, just because of what n squared possible combinations. So router designs have evolved over the last few decades through a few generations, 3 generations at least. You could say maybe 4, depending on how you count more recent evolution in data center style networks. Or at least the 3 of them that are recognized by the textbook, they're respectively memory-based fabrics, bus-based fabrics, and interconnection-based fabrics. Memory-based transfer from input to output port, these were the first generation old style routers. We don't really do this anymore. But if a packet's coming in, this is how it's going to work. It's going to be copied to actually a memory location that is accessible by all of the processes and all of the output ports. It's going to be buffered briefly, and then it's going to go to the corresponding output. Okay. So this is limited by the speed of memory. Memory speeds, they're much faster than accessing disk, as we know, but they're still very slow for packets. Okay, these packets, they don't have a lot of time. We're talking nanoseconds, possibly picoseconds if you're looking at hundreds of Gbps or hundreds of Gbps. So we quickly realized that we don't need to buffer these packets, and instead we can just do the switching through the interconnection based on a bus. So an input port, a packet coming in an input port can be written by the router onto a bus. Bus is just a fancy term for wire. Okay. And the output port can synchronously just receive that signal or sense that signal and read it off the bus. So there's no memory transfer. So there's that doesn't become a bottleneck. Your memory IOPS, operations per second, don't become a bottleneck, right? But switching by bus is also not fast enough. It sort of obviates a memory transfer. And so we very soon realized that we just need systematically a superior design in order to directly attack this n-squared complexity problem. And so that's where interconnection fabrics began. So this shows you an example of how an interconnection fabric can be organized. So what's happening here is that, so this input port to output port transition can happen in parallel with, let's say, this input port to that output port transition. As long as they don't share links, you can allow multiple of these connections to go in parallel. So you can have up to like n connections going in parallel, as opposed to with memory or bus, where only one can happen every single time. It's still not n squared, and that would be really nice. Everything can, no matter which input port it comes and which output port it does into, they can all go in parallel. That's still hard to do, but we don't know how to do that. But this is a significant jump compared to the previous two, right? The interconnection fabric. So here's an example of an n by n switch, n input port connected to n output ports. It's designed by recursively composing smaller switching fabrics into bigger switching fabrics. Okay? So in this example, if a packet comes in, it's on one of the input ports, the packet can actually be fragmented. This is an example of how a Cisco router might be organized, and in parallel be sent across multiple portions of this fabric. Each of those little things is very similar to this giant thing. So this by itself is a smaller n by n that we're using to construct a bigger, faster n by n, right? But the n's may be different. The n might be different here compared to n here, which in this example is 8 by 8. These could be like 4 by 4s or 2 by 2s. We also construct entire data center networks by just recursively composing smaller fabrics into bigger fabrics like this, okay? But routers have been following this interconnection fabric design for a long time. So here's an instantiation of an actual Cisco router. This is called a Cisco CRS router. There's 8 parallel planes or blades that are working all in parallel. Each of these blades has some set of input ports that it works on, the corresponding output ports it will send to. There's parallelism going on here, and by composing more and more of these blades, they have a significant amount of parallelism, right? It's not perfect, they're not embarrassingly parallel. That's the term used to describe a class of applications where you can simply keep on adding more and more resources, spend more and more money to get more and more speed. It doesn't quite work like that, but kind of gets there. And these kinds of switches can get you up to hundreds of terabits per second. Okay, that's a huge number. A terabit per second is 1,000 gigabits per second. So we're talking about hundreds of terabits per second. That's a huge number, right? So we can leverage parallelism in the design of these interconnection fabrics. This also gives you a little bit of a hint into why reordering in packets can happen. These blades are working in parallel. So these blades are sort of a little bit like threads in an operating system. They all are working on packets coming into input ports and putting them in output ports. So it's much harder for them to preserve ordering guarantees if they're all working in parallel. They can, but that has a cost. If you want to preserve the exact order in which they came on the output side, it's going to be a little slower doing that than doing it in any possible order, right? So this is why even though packets are not in a TCP flow, maybe taking the exact same route every single packet, there could be reordering just because switches are faster. They don't have to be put in first one first served. Now I told you that these are not quite embarrassingly in parallel. You can't just keep on putting more and more of these blades and getting proportionally more and more speed from these routers. Why is this? Well, we have to delve a little bit deeper into what's going on in this input port queuing. So in this example, that shows you at the input ports, 2 classes or 3 classes of packets that are colored blue, red, and green. And those colors tell you which output ports they are destined to. So all the red packets are destined to this output port. All the blue packets are destined here. All the green packets, no matter where the green packets come, they'll all be destined here. No matter where the reds come, they're all destined here. Okay? With input port queuing, unlike output port queuing, which we'll see in a second, you can have this problem called head of the line blocking problem. We've seen this term, head of the line blocking, before. Where did we see this term before?
HTTP.
Yeah, we saw that HTTP 2 alleviates this head of the line blocking problem by interleaving. Right? Quick in HTTP 3 also allows you to alleviate that problem in a different way. Okay? It's an application layer transport level approach. What's head of the line blocking? Like the term sounds, literally interpreted in English, you're blocked by somebody ahead of you in line. Okay? What's happening here is this green packet, there is nobody contending for this port right now. But it technically this switch could decide to take this green packet and just process it through the fabric here. But if you want to process the packets in the order they came here, you have to wait for this red packet to get its slot. And this red packet may not get an output port slot until this red packet has gotten its slot first. So basically the green packet, even though its output port was all clear, had to wait for potentially 2 red packets to be serviced before it got its turn. This is head of the line blocking. It's a waste of resources. You're not using resources optimally, right? If you had a scheduling algorithm here that looked at all of this and said, aha, I'm going to actually just wait to process this red, move this green ahead, and then put it here, then the completion time to process all the packets in the system will be lower onto this head of the line blocking problem, right? That's more complex. Okay, so output port queuing. There can be queuing in the output port. In the previous picture, we only looked at input port queuing examples. There can also be queuing in the output port. This is actually a more important type of queuing. This output port queuing is where you are now ready for transmission onto the wire and then propagation along the wire. Okay? It's just before that transmission point is where this output port queuing is happening. So you're almost ready to get on the wire. Any delay here, any loss here can be very costly. Just like in input port case, there's buffering that can happen. If the output port buffer gets full, the packet will be dropped. So you wasted not only all the time you spent across the network, but you also wasted the cycles you spent through the interconnection fabric. The output port queue cannot keep up the output. So this is your output port queue, and then this is the line along which the packets propagate. If this line is not fast enough and packets are arriving through the switching fabric faster than this line can accommodate, then the transmission speed of this line, then this buffer can also eventually get full and start dropping packets. Even if it doesn't drop packets, there's a question of scheduling. If packets come in here and get queued like this in the output port across the switch fabric, you always just do first come, first serve. You take the first packet, put it in the line, second packet, put it in the line. Usually, but not necessarily. The answer is it depends on your scheduling discipline. You may have prioritized processing of packets if differentiated services are in play. Or if your network service provider, your ISP, decides some customers are more special than other customers. It's very important. The slide is marked as very important because this has important ramifications on societal, economic, political policy. Right? People have heard the term network neutrality. What does that term mean to you? There's no wrong answer, just what does that term mean to you? Yeah.
I don't know a lot about it, like the
Yeah, yeah.
Ramifications for like users, including priority.
What was the outcry about? Like, what are people debating? What's the question? Yeah.
So having like a down payment for like your internet provider for like a month, let's say, like you gotta pay for like different services with the internet instead. That's what our the net neutrality is just paying for like internet in general.
Okay, it's along those lines. What's your name again?
Chris.
Chris. I saw a hand somewhere there.
I mean, the whole point is to have different services have the same kind of access and speed, delivery rate. But if we have different scheduling algorithms, we can prefer one service over the other. So the whole point behind net neutrality was all services have the similar kind of preference and should be given the same amount of scheduling time.
Yeah. So yeah, these are all answers along the right lines. It's really hard to define network neutrality, the problem and the disagreements therein in a single sentence. Those who will do it in a single concise sentence are probably politically motivated, giving you like a pithy tweet that makes you want to take that side over the other side. All right, so what am I talking about for those who haven't heard the term perhaps, right? Okay, so in output port queuing, you have a buffer like that. We have seen before that in TCP congestion control, that buffering is like salt. You need a little bit for taste, but too much makes the food inedible, right? You want to maintain some queue, but if the queue is very long, it will just cause increased queuing delays, and at some point packages are being dropped, which is even worse, right? So there is implicitly a trade-off between buffering a lot versus facing queuing delays. And in any case, if any packets are getting buffered at all, we need some buffering to keep the link saturated. If we're not buffering any packets, we're not sending fast enough, we're not even saturating the link, which means we're underutilizing our network resources. We have this question of how to pick packets here at the output port. Okay? We also have a question of what the buffer size itself should be. I'll explain first a thumb rule for how to size the buffer and then go to the scheduling, which has more to do with network neutrality. Okay? So people used to think that router buffer sizes should be the bandwidth delay product. It's the number of bits that could be in flight, the maximum number of bits that could be in flight along the wire. But for well over a decade, maybe more like 15 plus years, what we now know is when a lot of flows all mix together in a router, you actually don't need R2 times C of buffering. Instead, you need a lot less buffering because when you have a lot of flows, TCP-like flows, they're not behaving, from a router's perspective, this is not what's happening. From a router's perspective, if there's only one flow that can happen, but a router that's dealing with many flows might sort of see more fluctuations, kind of like this. Okay, they're much smoother than any one TCP flow might experience. And so the amount of buffering needed in this type of a network pattern, traffic pattern, is much smaller than this type of network traffic pattern. And so this much buffering suffices is the more common thumb rule, right? Okay, so let's go back to the buffer management, what kind of policies we can have. I'll first look at this technically, and then we'll ask this question of, well, okay, how does this relate to the network neutrality debate? This is all in the output port queuing. In input port queuing, your job is really just to determine the output port as quickly as possible. At the output port, you can have other scheduling disciplines. You can basically do just a tail drop discipline where the last packet coming in, if there's no buffer room, it gets dropped, and then beyond that, simply do SCFS, first come, first serve. Okay. You may also at this place do things like explicit congestion notification. Remember ECN I told you in transporting network assisted transport? Routers may mark some bits and packets to convey back to the sender that there's congestion in the network. Here's where you may mark some packets possibly probabilistically or deterministically, the queue size grows beyond a certain length to convey to the center that there's congestion. Okay, the disciplines here, these are very similar to your operating system disciplines. First come, first served is a very common one. Okay, you could say it's maybe the most common or the default policy. But you may have other kinds of policies beyond first come, first served. You may have prioritized packets where you have an animation for this, where the red packets go into a high priority queue, the green packets go into a low priority queue. So for example, if this is the traffic arrival pattern where there's a red packet followed by a green packet followed by a red packet, then the way in which they'll be processed, the first red packet will be processed, even though the second packet was green and arrived before the third red packet, the third red packet will be processed before the second green packet. This is what priority queuing will do for you. Okay? Those of you who have or are doing or done or are doing right now currently in operating systems course, you've seen that time-sharing operating systems have similar scheduling policies for sharing time across processes. So it's very similar in spirit to that. You can have other kinds of round-robin-like policies, which is another common default in time-sharing operating systems, which tries to give all processes roughly the same amount of time by taking one from here, taking one from here, and doing that over and over, right? Assuming that the queue is full. If some queue doesn't even have packets, it can jump over to the next queue. Okay, so you can see here that we're talking colors of packets, prioritization. So this, I'm going to just weighted paired queuing is just adding weights instead of uniform round robin, right? This is all should be familiar to you from your operating systems courses. The moment you see these different colored packets, gold, silver, bronze, or red, green, and so on, and some packets being treated favorably compared to others, some red lights should flash in your head, right? Is the President of the US's packets more important than your packets? Are Congressman's packets more important than yours? Is Tim Cook or Microsoft's Nadella, who's the CEO, are their packets more important than your packets? Who gets to decide this? Who gets to decide internet policies? Well, what is the internet? The internet is an internetwork of about 50,000 plus ISP networks. These are all independent corporations by themselves, or they could be not-for-profit organizations as well. There isn't something governing the internet on top of all this. So each ISP can decide what it wants to do, what policies, what scheduling policies it wants inside its own network. And so when people talk about network neutrality, they're talking about whether and to what extent packets should be distinguished or discriminated, depending on your point of view. Is it a service? Is it a bug or a feature? Is it a desirable service or is it discrimination? Okay. In airlines, you have any business that is in the business of transporting things is subject to some rules or laws, regulations and laws called common carriage laws. This is true for transportation, this is true for telephony, this is true for the internet as well. In airlines, we're very comfortable with the idea of paying more for business class, paying even more for first class, right? It doesn't seem like, that doesn't seem like discrimination. And there's implicitly some level of societal discrimination. If people who have more money can get better things in life, but most of us have come to accept that as normal, right? It's life. But common carriage laws for transportation networks are different from those for telephony or for the internet. Why is this? This also depends on region-specific policies, okay? Different countries, so there's no governing body for the internet. Different countries have different principles, right? Different notions of what democracy means in that country, what free speech means in that country. So they implement these, the laws are accordingly different, and whether or how they discriminate or distinguish or offer prioritized service for different packets depend on this as well. So we don't have a problem with people paying more for better service in transportation networks. We're very comfortable with that. But in the US at least, we get very upset about anything that impinges or touches on this topic of free speech. We all have a belief that speech should be free, but most people also recognize there should be some limits somewhere drawing a line, especially when it impinges, when it hurts somebody else, or it in turn may, counterintuitively, your free speech may reduce or impede the free speech of somebody else who's less privileged than you. Okay, that's where the debates really happen. I saw hands somewhere there.
Is packet scheduling and buffer management how your ISP throttles you?
Is packet scheduling, buffer management?
How your ISP throttles you? Like if they don't, like they want to slow down your service.
Oh, how your ISP control? Yeah. So of course, these mechanisms all exist in routers, right? The debate is under what conditions are we going to use them. So yeah, they can use these policies to decide which packets to load down prioritize. If you're sending too fast, then you decide they can give you a weighted fair queue share of the resources. So if there isn't anybody else competing for the resources, you can have your way. But if there's a lot of traffic, then your packets will start getting dropped, right? Yeah. So these are all mechanisms that exist and are used for, among other things, rate limiting. Rate limiting isn't even that unfair, right? It's not discriminating. It's just saying if somebody's saying too fast, we just giving equal share of resources. But by explicit prioritization, who gets faster, who gets lower packets? This comes down to the question of, well, does everybody get to make the same? Think about phone lines. Are everyone's phone calls treated the same, or some people's phone calls treated different? Even in telephony, you have common carriage laws that are very similar to the internet's. People recognize that communication is different. We want communication to be democratized as much as possible, right? And so, whether or not you can pay more for better service, some people think of that as a feature. They want it, they want faster service. But it can also mean that the likes of Netflix and Amazon and Google can negotiate contracts with ISPs where their packets get much better service, and then for a new startup, for a smaller business that's not as powerful, they simply just cannot compete with these bigger players who are much wealthier and who have effectively control over communication networks. So this is where just saying this is a feature and we should be able to pay for more service can impinge the free speech of others and can prevent them from getting to the same place, having the same opportunities as the more privileged ones have gotten to already. Right? So that's what the networking strategy debate is about. Technically, it comes down to output queue scheduling policies, like first come, first serve, weighted fair queuing of prioritization. Right? That's the end of the class today. We'll continue on Tuesday with the IP